For a 1000-foot primary direct burial application, a typical choice is a 3-conductor 500 kcmil XHHW-2 secondary aluminum cable. This type of cable is specifically designed for direct burial applications and typically has a voltage rating of 5 kV. When considering the price difference between direct burial and non-direct burial cable, direct burial cable is generally more expensive. The specific cost difference can vary based on the manufacturer and the precise cable specifications, but you can expect it to be approximately 15 to 20% higher. Regarding running other conduits in the same trench as the primary cable, which includes telephone and television conduits, it is generally not recommended. There are several reasons for this recommendation. Firstly, the primary cable carries high voltage and current. This high voltage and current can create electromagnetic fields. These electromagnetic fields can potentially interfere with other communication signals carried by the other conduits. Secondly, in the event of a fault on the primary cable, the intense heat and arc flash generated could damage adjacent conduits and cables. Thirdly, different types of cables often have different burial depths and installation requirement. This difference can make the trenching and installation process more complicated and increase the risk of non-compliance with regulations. However, there are exceptions to this general rule. In certain cases, it might be permissible to run other conduits in the same trench as the primary cable, but specific conditions must be met. Firstly, the conduits must be physically separated from the primary cable by a minimum distance. This distance is typically specified as 6 to 12 inches, but you should always verify the requirement with your local electrical inspector. Secondly, the conduit should be constructed of non-metallic materials. Common examples of such materials include polyvinyl chloride, commonly known as PVC, and high-density polyethylene, commonly known as HDPE. The use of non-metallic materials helps reduce the risk of electromagnetic interference. Thirdly, the conduits must be properly trenched and installed. This installation needs to be in accordance with all applicable codes and standards to ensure safety and compliance. It is crucial to emphasize that the best practice is to always consult with your local electrical inspector or your utility company. These professionals can provide specific requirements and guidance regarding the installation of primary cables and other conduits in the same trench, ensuring that the installation meets all safety and regulatory standards. When selecting the appropriate wire size for the primary conductors, several factors need to be considered to ensure safety and compliance with electrical codes. Firstly, determine the total load in amps that the three-phase transformer will supply. The questions specify 200 amps times 3 equaling 600 amps on the secondary side at the service entrance of each house, so consider that amount when determining the minimum amperage. Secondly, calculate the minimum ampacity of the primary conductors. The primary conductors must have an ampacity rating equal to or greater than the calculated load. The calculation must account for the transformer's voltage ratio and efficiency. For example, if the transformer is stepping down higher voltage to 208/120 volts, the primary current will be lower than the secondary current, but this needs to be precisely calculated. To calculate the primary current, use the formula primary current equals secondary voltage times secondary current divided by primary voltage times transformer efficiency. For example, consider a scenario where a transformer steps down 4,160 volts to 208/120 volts to supply a 600 amp load, and the transformer efficiency is 95%. The primary current would be calculated as follows: primary current equals 208 volts times 600 amps divided by 4,160 volts times 0.95, which equals 312 amps. Thirdly, consider voltage drop. Voltage drop is the decrease in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code (NEC) recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, select a conductor size that is large enough to carry the load current over the distance without significant voltage loss. The longer the distance, the larger the conductor may need to be. Use voltage drop calculators or consult the NEC tables to determine the appropriate conductor size based on the length of the run, the load current, and the conductor material. Voltage drop can be calculated using the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the constant for the conductor material, approximately 12.9 ohms for copper and 21.2 ohms for aluminum. I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils of the conductor. So, voltage drop equals 2 times 21.2 times 312 amps times 1000 feet divided by 500,000 circular mils, which equals 26.43 volts of drop. This drop is from one phase to neutral, or one phase to another phase. Now calculate the percentage of voltage drop with the following formula: percentage voltage drop equals voltage drop divided by source voltage times 100. So, percentage voltage drop equals 26.43 divided by 4160 times 100, which equals 0.63%, well below the maximum allowable 5% threshold. Fourthly, select the appropriate insulation type. For direct burial applications, the NEC typically requires conductors to be identified for direct burial use. Common insulation types for direct burial include XHHW-2, which is a cross-linked polyethylene insulation that is resistant to moisture and heat, and US-2, which is an underground service entrance cable. Ensure that the insulation is rated for the voltage and temperature requirements of the application. Fifthly, check the NEC tables. The NEC provides tables that list the ampacity of various conductors based on their size, insulation type, and installation method. Consult NEC table 310.15 to determine the appropriate conductor size for the calculated load. Be sure to apply any applicable correction factors for ambient temperature or the number of conductors in a raceway. Sixthly, consider the conductor material, which is usually copper or aluminum. Copper has a higher conductivity than aluminum, so it can carry more current for a given size. However, aluminum is lighter and less expensive than copper. When using aluminum conductors, be sure to select a size that is larger than the equivalent copper size to compensate for its lower conductivity. Seventhly, consider the environmental conditions, including soil conditions, moisture levels, and temperature. These conditions can affect the ampacity and lifespan of the conductors. In wet or corrosive environments, use conductors with appropriate moisture and corrosion resistance. Eighthly, follow the NEC guidelines for burial depth and clearances. The NEC specifies minimum burial depths for direct burial cables to protect them from physical damage. These depths vary depending on the voltage, location, and type of installation. Refer to NEC table 300.5 for the specific requirements. Ninthly, use proper installation practices, including proper trenching, backfilling, and compaction. Avoid sharp bends or kinks in the conductors, and protect them from rocks or other sharp objects that could damage the insulation. Tenthly, consult with a qualified electrical engineer or inspector. If you are unsure about any aspect of the conductor selection or installation process, consult with a qualified electrical engineer or inspector. They can provide expert guidance and ensure that the installation meets all applicable codes and standards. In the example provided, a 3-conductor 500 kc mil XHHW-2 secondary aluminum cable is mentioned. This is a common choice for primary direct burial applications. The 3-conductor indicates that the cable contains 3 insulated conductors within a single jacket. This is suitable for a 3-phase system where each conductor carries 1 phase. The 500 kc mil refers to the cross-sectional area of the conductor in thousands of circular mils. Circular mil is a unit of area commonly used to measure the size of electrical conductors. A larger kc mil value indicates a larger conductor size, which has a higher ampacity. The XHHW-2 is the insulation type. XHHW-2 insulation is a cross-linked polyethylene insulation that is rated for wet or dry locations and has a maximum operating temperature of 90 degrees Celsius. This insulation type is commonly used for direct burial applications because of its excellent moisture and heat resistance. The secondary aluminum cable indicates that the conductor material is aluminum. Aluminum conductors are lighter and less expensive than copper conductors, but they have a lower conductivity. As a result, aluminum conductors must be larger than copper conductors to carry the same amount of current. The 5 kV voltage rating indicates the maximum voltage that the cable can safely withstand. Ensure that the voltage rating of the cable is equal to or greater than the system voltage. The reference to consulting with the local electrical inspector or utility company is crucial. Local codes and regulations may vary, and the electrical inspector or utility company can provide specific requirements and guidance for the installation. Always follow their recommendations to ensure compliance and safety.